Alright, in this video for Math 1560 Calculus 1 at U of L for fall 2017, we're going to look at some of the properties of definite integrals. Okay, so first just a reminder how the definite integral is defined. We define it as a limit of Riemann's sums. And remember that each of the terms in this Riemann sum is the area of some rectangle, right? The height of the rectangle is given by evaluating the function at some point. The width of the rectangle is given by delta x, and we the way we set these up is once we have our interval, we set up a uniform partition into n subintervals. We evaluate our function at the right endpoint for each interval. We do this calculation, we add everything up, and we try to evaluate the limit. Now, in practice, there are very few functions that we can evaluate by hand using this method. This is the definition, but aside from maybe polynomials and even then polynomials of relatively small degree, you're not going to get very far trying to evaluate the integral using the definition. We'll see in the videos after this one that the way you want to tackle those integrals, the way you want to get those values is using the fundamental theorem. We're on our way there, we're not quite there yet. Also remember that if f of xi happens to be negative, then that particular area contributes a negative value to the sum, right? So it's a signed area computed by the integral. Now the first basic property, an important one, is that the integral is guaranteed to exist for every continuous function. So pick any function, doesn't matter how weird it looks, as long as it's continuous, you are guaranteed that that integral exists. We are not going to prove this theorem. In fact, the proof is quite difficult. If you are interested in seeing why this is true, you can pick out a more advanced textbook than the one we use, or you could wait a couple of years and sign up for Math 3500, our Analysis 1 course, and you'll see how things work there. Okay, so we know we can integrate continuous functions. What else do we know about the integral? Well, there are a number of nice algebraic properties satisfied by the integral. Now the first one just says that if the two endpoints are the same, then the integral is 0. Well, that makes sense, right? Because if the two endpoints are the same, then you're basically dealing with, a rectangle of 0 width, right? If you think in terms of area, right? If the width is 0, the area is 0. Okay, so that one is quite clear. The next one also is pretty straightforward, and I think for this one we won't even really we're going to try to show why some of these are true, but this one I think we can understand visually, that if you have a graph, right, and we start at A and we end at B, and so we're calculating this area. If we think in terms of area, if we choose some point C in between and we divide this up into two pieces, well, clearly the total area should be the area of the first part plus the area of the second part, right? So this is area 1 right here. This is area 2. So again, this is clear. Now, if you swap the limits, this is a little bit peculiar, because if you swap the limits so that if A is less than B, then suddenly your upper limit is less than the lower limit, and that's not exactly the context in which we define the integral. Nonetheless, you can still make sense of this. You can think of this as a convention just to make sure that the signs work out. We'll see places where it's necessary to have this. One way to think about it is simply that when you swap them, right, your delta x was b minus a over n, and then that's gonna go to, if we swap a and b, I go to a minus b over n, which is minus delta x, right? So swapping a and b changes the sign of the delta x, and so it changes the sign of the integral. And then the last two are just basic algebraic properties that mimic sort of the constant rule and the sum or difference rules for derivatives, right? If there's a constant inside the integral, you can pull it out. Integral of a sum is the sum of the integrals. And let's note here, we'll look at proofs, I think, for 4 and 5. We're not going to prove them, but we'll try and sketch the ideas of why these should be true. Property 2 works even if let's say c is less than a. For c less than a, and we want to show that we could still say that the integral from a to b of fx dx is equal to the integral from a to c of fx dx plus the integral from c to b of fx dx, right? Well, okay, so this is what we want. So how do we see that it's true? Well, one thing we could say is, okay, if c is less than a, if we're in this case, then c is less than a is less than b. And so what we could say, using 2, is we could say that the integral from c to b of fx dx is equal to the integral from a to b, or sorry, from c to a, because a is in between, plus the integral from a to b. And then I can subtract this part from both sides. And what happens when that comes over? Well, when that comes over, I'm going to get the integral from, I'm going to get minus the integral from c to a plus the integral from c to b equals the integral from a to b. Right? But now if I use property 3, right, that minus sign flips the limit, so this minus becomes the integral from a to c, right, and so this is going to turn into that using property 3. And a similar argument would show you that property 2 holds if c happens to be bigger than b. So this is a useful property sometimes for splitting up integrals into different pieces. Alright, so let's look at, we've convinced ourselves, I think, that 1, 2, and 3 are valid. What about 4 and 5? So let's think about, well, what's the integral from a to b of k times fx dx? Okay, well, by definition, that's the limit n going to infinity, sum I going from 1 to n of k times f of xi times delta xi, right? But that k is a constant. It's a constant multiple, so I can factor it out of my sum. Oops, that n looks a little bit too much like an h. So n going to infinity of k times the sum I going from 1 to n f of xi delta x. So we're using uniform partition, so we don't need xi here. But then, of course, we also know that you can pull constants out of limits. So we could write this as k times the limit n going to infinity of our sum I going from 1 to n f of xi times delta x, which is k times the integral from a to b of fx dx, right? And then a similar argument works for, say, for example, the sum rule. For the sum rule, well, you're gonna when you're doing this integral, the integral from, you know, of f plus g. What do? Well, you're gonna use the sum I going from 1 to n f of xi plus g of xi times delta x, but we know that that could be written as the sum of, push the delta x through, f of xi delta x plus g of xi times delta x, and we also know that we can split that sum up into two individual sums, right? F of xi times delta x, and then the sum I going from 1 to n g of xi times delta x. Okay, so the limit of our original sum, the limit of that sum as n goes to infinity, gives me the integral of the sum. And if I take the limit down here, well, we know that the limit of a sum is sum of the limits, and the limit of this gives me the integral of f. The limit of that one gives me the limit of g, right? So basically, some of these, algebraic properties for integrals, they're just inherited by corresponding properties for sums. There are a couple more properties worth mentioning. There are certain comparison properties. Okay, one is simply that if you have two functions and you know that one function is always bigger than the other, then the integral of that function will be bigger than the integral of the other. So inequalities are preserved by integration. If f is less than g, the integral of f will be less than the integral of g. Again, this is fairly easily understood in terms of areas, right? If you're comparing rectangles of equal width, then the rectangle which is taller is going to have a larger area than the rectangle which is shorter. And a particular example of this is if you have bounds for your function. If you have, say, an absolute min and an absolute max, right? So we have this sort of inequality. M and the little m and the big M here are constants. Well, notice that whenever if you want to integrate a constant, integral from a to b of a constant, right? What is that? Well, that would be the limit, n going to infinity, of the sum, I going from 1 to n, simply a constant times delta x. Oh, well, what is that? That's the limit, n going to infinity of a constant. Pull the constant out of the sum. What's delta x? Delta x is simply b minus a over n. What do you get? You just get the constant times b minus a, because if you add b minus a over n to itself n times, you simply get b minus a. Right? So if you integrate a constant, you simply take the width of the interval multiplied by the constant, right? All we're doing here is area of a rectangle. That's all it is, right? Here's your constant value a, b. We're calculating this area of a rectangle. We'll see that this particular inequality is going to come in handy for us understanding the fundamental theorem of calculus. And finally, we have the triangle inequality. We don't really need it very much in this course, but it is something that pops up from time to time, so it's worth mentioning. Taking the integral and then doing the absolute value gives you a result which in general is less than or equal to what you get if you do the absolute value first and then do the integral. So those are all the properties that you need to know for the definite integral. In the next couple of videos, we're going to look at the fundamental theorem of calculus, which is going to allow us to start actually computing integrals.